real gases. Well, ideal gases, there's no attraction between the gas particles, and the particle volume is so small we can ignore it. In a real gas, we observe that they behave like ideal gases under many sets of conditions, but under high pressure or low temperature, they do not. So here's a graph that shows the molar volume of several real gases at STP. Here's the ideal gas, 22.41 liters. And we see chlorine, carbon dioxide, ammonia, nitrogen, helium, hydrogen. They're all very close to an ideal gas. Now, chlorine and carbon dioxide are the most off, but these guys are really, really close at standard temperature and pressure. If we go to low pressures, the volume of argon gas is the same, nearly identical to that of an ideal gas. When we increase the pressure, though, what happens? We're pushing the particles closer together. As you push those particles closer together, the size of the particle begins to matter more and more and more. So if you take those people in Wyoming and you start to round them up and you herd them into a smaller and smaller area, that's the equivalent of increasing the pressure on a gas. At some point, the size of the people starts to matter. So we see that at high pressure, the molar volume of argon is larger than what is predicted by the ideal gas law, because the particles themselves are occupying some volume. So we can look at graphs like this. Here, the red is an ideal gas, and what color is that? Blue or green? I think it's green. The green is argon. As we increase the pressure, the volume of argon becomes larger than what's predicted by the ideal gas law. And that's because the volume of the particles is becoming significant at higher and higher pressures. And the difference between these two lines is going to just continue increasing as you increase the pressure.
So they'll continue to get farther apart?
The lines will continue to get farther apart. There's a limit to how much pressure you can put on argon and still have it be a gas. Because at some point you press them so close together that it becomes a liquid, and then you can't compress it anymore. And so then things get really strange. An ideal gas, because it has no volume essentially of particles, an ideal gas could be compressed to zero volume.
So like given enough information, then could we find in that point where they'll be farthest apart before they turn into liquid?
You could. I don't think it would be worth the effort, because it would vary so much depending on interactions and conditions. So back in 1873, a guy named van der Waals adjusted the ideal gas equation to account for the real behavior of gases. And we're not going to do calculations with this on an exam. There might be one or two on homework questions. But I want you to know that there are ways to calculate the actual volumes for real gases under conditions where their volume matters. So it adds NB, where B is van der Waals constant, and that constant is going to be different for each particular gas. It's going to be individual to the gas. You add that factor on, and that will help you to predict the actual volume of that gas. We also see an effect when we get to low temperatures, and this has to do with intermolecular attractions. In an ideal gas, there's no attraction between particles. And this is true of real gases at relatively high temperatures, reasonable temperatures, because the gas particles are moving fast. Like that one was 238 meters per second. Those are moving fast, right? That's like passing people on the highway, right? You barely see their car. You're definitely not going to notice if they're attractive or not. But at slower speeds, like, people used to cruise Blackstone. I think they finally put an end to that. But when I was growing up, people used to go cruise Main Street in the town that I lived in. And, the teenagers would get in their cars and they drive down. You're driving really slow and you can get a really good look at the people in the other car and things would happen, right? There were interactions between the people. Some of them were positive and some of them were negative, right? But at high speeds, there's no interaction. So what happens with gases is gases are more like people, real gases. When they're moving slow enough and they bump into each other, there are interactions that occur. And that causes the gases to behave slightly differently. So what we see is at low temperatures, the gas atoms spend more time interacting with each other and less time colliding with the walls, and so the actual pressure is lower than what we expect. Because they bump into each other and they exchange a few words, oh, hi, how are you, before they go off. And so there's less pressure at these low temperatures than what we expect. So van der Waals also made an adjustment for this, and this uses another van der Waals constant, A, again, different for each gas, and this gets thrown in. So the pressure is going to be nRT over V, and then you have to subtract this correction value. There's a table of some van der Waals constants for common gases. And if you put those into the ideal gas law, you end up with this mess. But this can be used to calculate volume or pressure of a real gas pretty much under any set of conditions. If we plot PV over RT for 1 mole of gas, the ideal gas law predicts that PV over RT will be 1. But what we see for real gases is that for some of them, it's higher, and for some, it's lower. The curve being lower than ideal means that the most important factor is the intermolecular attractions. And so water is lower. There are some significant intermolecular attractions between water molecules. Helium doesn't really have intermolecular attractions, even at low temperatures. If the curve is higher, it means the most important factor is the molecular volume. So the volume is more important than interactions.